Hi, today we'll be demonstrating for you the color changes that a few common indicators make when they're placed in acids and bases. So what we have here is this spotting tile, and in this column here we are having acidic solution, and in this column here we are having basic solutions. And the indicators that we'll be using today are as follows. We look at the effect of acids and bases on phenolphthalein indicator. Put a drop of phenolphthalein in acid and see what color it has. We can see that's colorless, okay? And then we drop it inside base and that's pink. So phenolphthalein is colorless in acids. It goes pink in base. Bromothymol blue in acid. Let's see what's it called in acid. In acid, bromothymol blue goes yellow, and in base, it stays blue. Next, we'll use bromophenol blue. First of all, put a few drops inside the acid. Just like bromothymol blue, it goes yellow, and in base, again, like bromothymol blue, it stays blue. Find the difference. And then we look at the effects of acid and litmus paper. So here we're having pieces of blue and red litmus paper. Put that in acid. We can see it has no effect on the pink litmus paper, but it causes blue litmus paper to go pink. All right? Now we look at the effect of bases and litmus paper. So here we have piece of red and blue litmus paper. Let's see what happens in base. We can see that the blue litmus paper remains blue, or it turns brighter blue, but the red litmus paper goes blue. So what we'll do now, fill this table on the board. Here is colorless, and litmus here in acid, litmus is pink, and in base, it is blue. Okay? Those are the color changes that are made for these common indicators. Of course, we have a series of indicators, and they will have different colors in acids and bases. I want to demonstrate for you what a acid-base neutralization reaction looks like. But before we do that, I want to review with you what a neutralization reaction is. As can be recalled, a neutralization reaction is the reaction between an acid and a base to give you salt and water. Here you're seeing an acid reacting with the base to give you things that are neutral. The salt and the water formed there, especially when salts and water are formed between the reaction of strong acids and strong bases. You get a salt that is neutral. Of course, water is also neutral. The reaction that we're exemplifying here is that between hydrochloric acid and potassium hydroxide to give you potassium chloride and water. We can break that into its ionic equation, break that into the hydrogen ions, chloride ions, potassium ions, hydroxide ions, potassium ions, chloride ions. Water we do not break up because that's a molecule. And then we remove the spectator ions. Chloride ions are common on both sides. Potassium ions. Effectively, what is happening here is hydrogen ion and OH ion reacting to give you water. Recall from the Arrhenius theory, an acid really is caused by H plus ions, and a base is caused by the OH ions that are present there. Now look what is happening. The hydrogen ions are combining with OH ions to give you something that is neutral. All the other things that are involved are not important. This is the important thing that is happening. Hydrogen ions are reacting with OH ions to give you water, and this is a neutral substance along with the salt that is neutral. So that's, in theory, is what a neutralization reaction is all about. What I have in this test tube here is a small sample of an acid. Now we want to neutralize that by this basic solution here. But we know, as can be recalled, during a neutralization reaction, which we said is a double displacement reaction, you do not see any visible change. So if I pour that base into this HCl here, how would I know when neutralization point is reached? And this is where acid-base indicators come in very useful. So what I'll do, first of all, I'll pour 2 drops of this phenolphthalein indicator into this acid here. Okay. As can be recalled, phenolphthalein acid is colorless. So gradually what we'll do now, we'll drop some of this base inside of this solution here. The fact that it does not go pink as yet indicates that at this point in time, there is still excess acid inside here. It will not go pink until all the acid has been neutralized by the base. So we keep doing that. See, there's a tendency for it to go pink now. It means that the end point is about to be reached. More and more salt and water is being formed. Okay. More of the acid is being neutralized by the base. When you see that pink color persisting there, it is indicating to us that the end point of this neutralization reaction is about to be reached. Okay? See, it's coming there now. 1 drop more. That's because we need to mix it up well. It's showing at the top because the base is at the top and it's not catching the acid at the bottom there. Okay? So you can see that the solution stays pink now. That indicates to us that, you know what, all the acid has just been neutralized and now we have a drop or so more of the base that's left in excess. This solution will stay pink. Maybe you drop 1 drop more to get a nice pink, deep pink color. All right. So it stays. That means neutralization has just happened, but we have a slight excess of the base. What do you think will happen if we now pour a few drops of acid inside? Let's see what's happened. What do you think is going to happen? Why did that happen? Because the acid was able to neutralize the little bit of excess base there, okay? And now the acid is left in excess. And we can keep doing this all the time, right? We can now pour a few drops of the base inside, neutralize that acid there, and then leave 1 drop in excess to show you that the neutralization process has happened. So this is how acid-base indicators are useful in enabling us to know when the endpoint of a neutralization reaction is reached. Okay? I hope that was useful. All right.